Hi, it's Miss Dagenford again, and I wanted to continue our discussion and continue our learning in carbon chemistry in carbohydrates. So the other video, I showed you that there were four main organic families. So we're going to talk about carbohydrates and lipids in this video. And that's because carbohydrates and lipids, well, they both have carbon, hydrogen, and oxygen, and yet they differ in some really significant ways. And so by the end of this video lesson, you should be able to tell me the the characteristics of both carbohydrates and lipids and what makes them carbohydrates and lipids. Their defining characteristic. What makes them carbs and lipids. So let's get started. So carbohydrates are something that you are probably familiar with. You know they're sugars. Maybe you've taken a nutrition class or a health class in your middle school days where you talk about carbohydrates. Now, carbohydrates are also known as sugars and starches. And so, what they have all in common, all carbohydrates have a 2-to-1 ratio of hydrogen and oxygen. Always. That's what makes them carbohydrates. So notice our formula here, C6H12O6, 2-to-1 hydrogen to oxygen. If I had C5H10, it would be O5. Always, it doesn't matter. If I give you H22, you should tell me it's O11. It's 2-to-1, always. And in fact, there's a clever way you can remember this. Notice the word carbohydrate. Hydrate is water, right? Hydrated. And water is H2O. So ding, ding, ding. Nice way to remember carbohydrates. Now, so that's one distinguishing characteristic of carbohydrates. The other distinguishing characteristic would be that they are all polar. They all mix with water. And that is the hallmark of carbohydrates. You can put sugar in your tea. Your glucose dissolves in your bloodstream, and that is the characteristic of carbohydrates. They mix well, and it's because of all of those oxygen and hydrogens that make them polar. Now, carbohydrates are divided into three levels. We have monosaccharides. Again, mono means one. And so notice, why do we say one here? Well, we only have one ring in this glucose. And that's what you're looking for. One ring of carbons. Now, you might think to yourself, why did she just say carbon? I don't see carbons except for this one right here. But remember, or note that in organic chemistry, because we're dealing with large molecules, we oftentimes can kind of sneak away the carbon in writing it because, well, that just makes it cleaner. So everywhere my pointer dot is, right there, there, or right there, and there. That's a carbon. We're just making it a little cleaner. So monosaccharides are distinguished by that ring of carbon. And then in the purple one, this is just a ring of carbon, but they've been connected in a pentagon instead of a hexagon. But that's your hallmark pattern. That's what you should be looking for, is a ring. And if it's only one, then it's a monosaccharide. Now, do you need to know the difference between these three? Like, am I ever going to give you a matching where I say, ooh, which one is glucose, which one? No, I will not do that to you. You don't need to be able to tell me like which one's which, but you should know that glucose and fructose and galactose are monosaccharides. And we'll be doing some practice with that. Now, if I gave you a picture of galactose, you should be able to say that's a monosaccharide. So you should be able to identify a monosaccharide. If we put two monosaccharides together, we get a disaccharide, meaning two. And so a disaccharide, we connect them through the oxygen. And I like to think they're holding hands. And so you've got one glucose over here and a fructose, and they're holding hands in the middle. Aw. And so the disaccharide has two rings, the green and then the purple, two rings. And then over here, there's another type of disaccharide. Again, you don't need to try to figure out which one's which. You just need to be able to recognize this is a disaccharide. Now, there are a couple of disaccharides you've heard before. Lactose is in milk. Sucrose is in plants. Plants make table sugar, right? So if you are baking and you have a cup of sugar, well, that's sucrose. Disaccharides and monosaccharides are fantastic forms of quick energy, and your body really does like them for that quick, easy burst of energy. All right, so the last one, and boy, are these big molecules. These are polysaccharides. There are three of them: glycogen, starch, and cellulose. Now, glycogen is something we make. So when you are building your glucose molecules together, you're building glycogen. And it's this middle one, really long chains. Notice monosaccharide, 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 monosaccharide. Watch my pointer. Monosaccharide, monosaccharide, glucose, 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 glucose. That's all they are, is glucose molecules stuck together, holding hands, and that makes a polysaccharide. Starch is something plants use to store their energy. So right now, as the plants, the trees are pulling down their sugars off out of their leaves, they're going to make starch molecules. And and we store glycogen in the muscles and liver, and that's what you use. Like during a game, you're going to pull the glucose molecules off, much like beads on a chain. You're going to pull the individual glucose molecules off and use it during your game. That's how you do. That's how you work. So both of these are polysaccharides, and then the last one, cellulose, is also a polysaccharide. It's a little different because it's not really used for energy. It's used to make the plant cell walls. And so we call that fiber. We also know that as fiber. So those are the polysaccharides. Most of them deal with energy, except for cellulose. The longer chains are just more for storing energy, but they're not the best one for storing energy. The really good ones are lipids. So we're switching gears. Notice I changed the color of my background here. These are lipids. Lipids don't really have the monomer thing going on, but we do have a couple of categories we want to go over. Lipids also have carbon, hydrogen, and oxygen, but they have very little oxygen, as opposed to the carbohydrates. So notice if I swing back, notice all of those oxygens in those monosaccharides. A lot of oxygen, 2-to-1 oxygens. But notice if I go to that big triglyceride here, there's no oxygen at all, except for right here, that's it. But in this long chain, there's no oxygen. Now that makes them, notice I put it in bold here, that makes lipids nonpolar. Oxygen, the water molecules are not going to be attracted to fats and oils. So there are three types of lipids I want to have you understand: fats, phospholipids, and steroids. But notice they're all going to have those characteristics. Very little oxygen, they're nonpolar. So the first one, fats or triglycerides, well, that's what we know as fats and oils in our nutrition or health classes. They're incredibly good at storing energy. They get a bad rap in our nutrition ideas, but that's because we don't use them well, right? But they're fantastically good at storing energy. And that's what our body does, is it stores any extra calories as triglycerides. Now, notice the big characteristic are these long chains of carbon and hydrogen. That is the definition of a triglyceride. And animals store any excess calories as fat molecules. Now, animals store it as saturated fats. Now, notice the pattern here. Saturated fats have all of the carbons attached to hydrogens. It is saturated. And they're solid at room temperature. Just remember the S's, solid, saturated. That would be things like bacon fat or butter or cream that solidifies. Anything that is solid at room temperature is a fat, a saturated fat. And then unsaturated fats would be oils. So they're defined by a double bond. They have this little space here. They're unsaturated. They don't have as many hydrogens around the carbon chain. That makes them have a little bend to them, and that makes them liquid at room temperature. So saturated, unsaturated. And then the last two, just want to go over quickly. There's not going to be that much information we need to know now. Phospholipids also look like they have those long fatty acid tails. But the weird thing about phospholipids is they've got this third group down here that's actually polar. These gray tails are nonpolar, but they have one little section that is polar. It's kind of weird. We'll go over them when we get to the membrane. Steroids are also not for energy. They're going to be for the cell membranes or steroid hormones. And they get a bad rap as well because we think of like athletes that have abused steroids, but really it's a class of molecule. It's not a bad thing. So for instance, here's cholesterol, and notice the pattern. We've got the hexagons, and then the fourth one is the pentagon. That's the hallmark. All steroids have this backbone, 4 rings that are fused together. And notice they're not holding hands. There's no oxygen in the middle. It's just 4 rings that have kind of been smushed together. So things like testosterone, notice the name, testosterone, steroid, progesterone, those are all steroid hormones. So that's going to be our video lesson for carbons and lipids. You'll have a chance to practice these, so have your slides out and so you can use them.